Selamat sejahtera, nama saya Devendran anak KISHON, nombor kilometrik B13241005.
Salam sejahtera, nama saya YUGESWARAN RAMESH, nombor metrik saya B1324100109.
Selamat sejahtera, nama saya SUBATHEERAN, nombor metrik B1324100014.
Selamat sejahtera, nama saya KISHON LETCHUMANAN, nombor metrik saya B1324100034.
For the theory, the disc brake as a metal disc or rotor instead of drum. It used a pair of flat, lined shoes or pad that force against the rotating disc to proceed braking. The pads are held in a caliper that stellate the disc. The caliper has one or more pistons which a seal and dust boost for each. During braking, hydraulic pressure behind each piston push it outwards. This forces the pad into contact with the disc. The resulting friction contact slows the stop the disc and wheels. If pads on the one side are worn more severely than one opposite side, the piston may be stuck in the cylinder of the opposite caliper. Brake discs should always be renewed or refinished in pair, both front and rear. Even if only one is damaged or defect, never renew the pads on one wheel only. Also, the dust created by the brake system may contain absorbers which is harmful for your health. Never blow it out with the compressor air. Its approved filtered mask should be worn when working on the brakes. For the first part, we start with making the disc rotor in CATIA B5. The disc rotor is made within regular specification of a vehicle. The disc rotor is made with 3 different materials. The reason of using 3 different materials is to find which material is more suitable for use in a vehicle.
Next, we will talk about the findings from our experiment of disc rotor with different materials under a certain load. First, we shall see the material properties of each material. Each material has different material properties. For iron, the Young modulus is 2.11 e to the power of 0.11 Newton meter square. The Poisson ratio for iron is 0.291. The density of iron is 7,870 kilograms per meter cube. The thermal expansion for iron is 1.21 e to the power of negative 0.05 over Kelvin degrees. The yield strength for iron is 3.1 e to the power of 0.08 Newton meter square. Next, for steel, the Young modulus for steel is 2 e to the power of 0.11 Newton meter square. The Poisson ratio for steel is 0.266. The density of steel is 7,860 kilograms per meter cube. The thermal expansion for steel is 1.17 e to the power of negative 0.05 per Kelvin degrees. The yield strength for steel is 2.5 e to the power of 0.08 Newton per meter square. Next, for aluminium, the Young modulus for aluminium is 7 e to the power of 0.10 Newton meter square. For the Poisson ratio of aluminium is 0.346. The density of aluminium is only 2,710 kg per meter cube. The thermal expansion for aluminium is 2.36 e to the power of negative 0.05 per Kelvin degrees. And finally, the yield strength for aluminium is 9.5 e to the power of 0.07 Newton meter square.
Okay, now we are going to see the results for the various material, which is iron, steel and aluminium, and we have conducted two type of forces, which is 1350 Newton and 1500 Newton. For the first one, now we are going to see the iron. The maximum wound missile stress we got it is 1.6 e plus 0.05. The unit is Newton meter square, and the minimum wound missile stress is 412, which is the unit Newton meter square, and the transnational displacement we got it 5.93 e minus 0.05, which is the unit is mm. And the result for the 1500 Newton, the maximum wound missile stress that we got it is, the value is 1.78 e plus 0.05. The unit is Newton meter square. And then the minimum wound missile stress is, we got it, the value is 458. The unit same as the, which is Newton meter square. And the transnational displacement, the value is 6.59 e minus 0.05. The unit is mm. And the safety factor, which is we done using the yield strength divided by the maximum wound stress. For the first one, which is 1350 Newton, we get it 1.76, and the result, the safety factor for the 1500 Newton, we got it 1.67. Next, we are going to see the results for the steel, which is we conducted the same as iron before. For 1350 Newton, the maximum wound stress is 1.62 e plus 0.05. The unit is Newton meter square. Minimum wound missile stress, the value is 340 Newton meter square. And then the transnational displacement 6.18 e minus 0.05 mm. The results for 1500 Newton, maximum wound stress is 1.8 E plus 0.005. The unit is Newton meter square, and the minimum wound misses stress is 378 Newton meter square. And then lastly, transnational displacement 6.87 E minus 0.005 mm. The safety factor that we have got it for the steel is 1.57 for the 1350 Newton, and 1.49 is for 1500 Newton, which is compared to the iron, this shows the better one than the iron. Lastly, we're going to see the aluminium. The results for the 1350 Newton is the maximum wound misses stress is 1.56 E plus 0.005 Newton meter square, and the minimum misses stress is 571 Newton meter square, and the transnational displacement is 0.000181 mm. And the results for 1500 Newton, maximum wound stress that we get it is 1.73 E plus 0.005 Newton meter square. Minimum wound stress is 635 Newton meter square, and transnational displacement is 0.000201 mm. And the safety factor for the aluminium that we get it is 3.55 for the 1350 Newton, and 1500 Newton we get it 3.38, which is compared to iron and steel, these get a higher value than the iron and steel. So as a conclusion, I would like to say that steel is better material for disc that we made.
Next, we shall go into the discussion. Based on our results, now we can compare the maximum von Mises stress of the materials. As we can see, the maximum von Mises stress for iron, steel and aluminium are different. For iron, the maximum von Mises stress is 1.6 E to the power of 0.005 Newton meter square, while for steel is 1.6 E to the power of 0.005 Newton meter square, and for aluminium is 1.56 E to the power of 0.005 Newton meter square. So all the von Mises stress for different materials, as we can see, are different, and the highest von Mises stress, as we can see, is for steel. Although so, if we compare the factor of safety between the different materials, we can see that aluminium has a factor of safety of 3.55. For steel is for iron is 1.76, and for steel is 1.57. So based on this information, we can do a small conclusion.
Based on our experiment, the steel material disc rotor is the best material to be used in a vehicle, as it the highest value of maximum von Mises stress can be handled and is the highest safety factor value. This shows that steel material can handle more endurance and wear compared to the other materials. In conclusion, we have successfully managed to design a brake rotor in virtual reality environment and provide the platform to visualize and optimize its structure and function aspect. It has also allowed us to find out which material is more suitable to be used by making a virtual load to be test each material.